Take off my mask. Good morning, everybody. My name is HAENGGI from Chalmers University, and I will be chairing this morning's session. In the morning, we have three speakers. Our first speaker will be Professor Martin HAENGGI, who's a professor of electrical engineering, as well as of applied and computational mathematics and statistics at Notre Dame. Martin obtained a PhD in 1999 from ETH Zurich, and then did a short stint at UC Berkeley before joining Notre Dame. Martin received a number of very prestigious IEEE Best Paper Awards. He's a fellow of the IEEE, and he was also the editor-in-chief for Transactions on Wireless Communication between 2017 and 2018. His scientific interests include networking and wireless communications, with emphasis on cellular, heterogeneous, vehicular, amorphous, ad hoc, cognitive, and sensor M2M networks. So please join me in welcoming Martin HAENGGI for this first presentation. Please.
Thank you very much, Hank, for the detailed introduction, and Francois and Andrea for the invitation. It's good to be back in front of a live audience now after a break, and in particular in Paris. So I'm starting with a yes.
You don't see your face. So
Oh, I need to. Okay. Okay, I need to. Yeah. So we start with a theoretical topic now that is tied to stochastic geometry. There will be a couple of other talks using the same kind of tools. So this is joint work with my former student Jayaraj, who is now at Qualcomm. And yeah, there's a link to the slides now if you want to download these. So these are the two goals now for this line of work or this talk. On the one hand, we'd like to achieve generality in the network modeling. On the other hand, in terms of the analysis, we want to have a strict reliability, as it might be important, in particular in vehicular safety messaging. So how do we achieve this? So these are the three tools here in yellow. On the one hand, we have a concept that we call transdimensional modeling that allows us to achieve generality while maintaining tractability. On the other hand, to assess reliability guarantees, we use what we call meta distributions. And it just so happened, the first time I talked about meta distributions was 7 years ago at another event that Francois organized now at UT Austin. So this work is based on these two papers with Jaya, that appeared last year, plus some background on meta distributions. It's in these two communication letters that also appeared last year. So first we start with the street systems that vehicles might lie on. So this is a more or less typical set of streets. And we realize it's very complicated. So we have short streets, long streets, bend streets, and we have intersections of different levels, T-junctions, four-way intersections, and so on. And of course, if we want to do anything mathematically, we need to find a mathematical abstraction that allows us to do theory and analysis. So quite generally, we can think of a street system as a random measurable subset of the plane that has no area, so the Vehic measure in 2 dimensions is 0. It contains no isolated points. There is no street, that's just a point. And we would like it to be stationary, for tractability, which means that if we take the street system, intersect it with any Borel set, and we are looking at the expected street length in that set, it should be proportional to the area of that set with some proportionality constant tau that denotes the mean total street length per unit area. And a prominent example is a Poisson line process, which is essentially just kind of a uniformly random set of lines that are spread on the plane. And specifically, we can take a homogeneous Poisson point process on this cylinder. That's the real line multiplied with the 0 to pi interval, where the xi's denote the shortest distances to the origin, and the orientations are phi I. And we'll hear a lot more about this kind of model specifically from Chang-Sik and later Harpreet. Another model is what we call a Poisson stick process. Now, so we throw down random points, again, according to a Poisson process, and then centered at each point, we put a line segment of a random length independently with a certain probability density. So this would give finite street lengths, and this would be with streets full of infinite length. And then on top of that, the natural kind of first order model is to put independent Poisson processes on each line. So in other words, the vehicles are going to form a Cox process that is supported on the street system. So its random intensity measure is given by the common intensity of all these Poisson processes multiplied with the one-dimensional street lengths in the set B. So overall, this vehicular point process is going to have density tau times lambda, the kind of the street length density times the density of vehicles on each street. So here is an illustration. On the left, we have this Poisson line process, Poisson point process, where we put Poisson processes on each line, and each line is of infinite length. And if we take sticks, now we have sticks of different lengths, and we put Poisson processes on top. And naturally, there are very short streets that might have no points, and there are even longer ones that have a positive probability of being empty of vehicles. We also recognize that in both models, we either have just vehicles on streets, or we might have, if we're lucky, we get vehicles close to an intersection. But in any case, these two street systems, they only have standard four-way intersections. Now there are no T-junctions with probability 1 here. Now we can decompose this street system into intersections or individual points of different orders. Now, one way to do that is using this definition. So we take a smaller and smaller ball, and we're wondering in the limit, if we make the radius of this ball go to 0, what is the asymptotic behavior as a function of the radius of that ball? So that gives us a parameter m here, that's a natural number. And in doing so, we have P1 are the endpoints of the streets. So if we put a little ball there, then the number of vehicles can only grow in one direction because we are at the end of a street. P2 are the interior points along a line or a line segment. So these are kind of the general points. P3 would be T-junctions. Now from the T-junctions, we can go in 3 directions, and then we have 4-way intersections and so on. So naturally, this set P from 1 to some arbitrary number forms a partition of the street system. And P2 corresponds to the street system almost everywhere because all the other points are discrete. So in other words, except for P2, all the others are countable, and they form themselves a simple stationary point process. So if we look at the intersections here, there we have a point process. Of course, that's no longer Poisson. All the intersections here are point processes, as well as the endpoints here are point processes. And then we can characterize the street systems based on the kind of points that appear in the street system. So for example, in the Poisson line process case, we have a 2-4 street system because all vehicles are either general or at the regular 4-way intersection. In the stick model, we also have endpoints. So we have 1, 2, and 4 that appear. All the other PMs are empty. And naturally, I mentioned T-junctions before. The question is how would we define a model that actually gives rise to T-junctions? And that is not as trivial as one might think. So here is a possibility. That's something we call a Poisson lily point model. So we start at points of a Poisson process, and then we start to grow line segments in both directions in some random orientation. And we stop when the line segment hits another line segment. So here, this started here, and then it grew until it hit this one. Then when it hits this one, it also stops on the other side, and similarly for all others. So naturally, this is a model where we have T-junctions, so points of order 3 and endpoints. In fact, every line segment on one end is an open end, on the other end it is a T-junction. Now, of course, this setup introduces a dependence between the street lengths. Now, that makes it harder to analyze. It's also interesting to see that this leads to a concentration of the number of vehicles in an arbitrary set. Now, why is that? Because when we have a dense region of Poisson points to start with, then the streets in that region tend to be short because they bump into each other quickly. And short streets means fewer points, no, because the number of points is proportional to the street length. On the other hand, if we are in a sparser region, the streets tend to grow longer, no, and then we have more vehicles among them. So the number of points in a set B is going to have a sub-Poisson distribution. We use a very simple transmission model here. So each vehicle transmits with probability P in a time-slotted system, and the vehicles that receive, they attempt to code a message from a transmitter that is at fixed distance D. So that is an Aloha type model now with fixed link distance. And what we would like to analyze now is the signal to interference ratio for a vehicle now that is conditioned to lie at the origin. So we have a distance-based path loss component, we have a random fading component, so that gives the desired signal. And then on the other hand, in the denominator, we have all the interfering powers, now where the BC factors, they represent the Aloha, so these are indicators that are Bernoulli with mean P, and then we have the fading and the distances. So we would like to know the distribution now of this random variable, so that's the SIR complementary cumulative distribution. Is also often called the success probability because it quite well represents the probability of a transmission success. Now, so we have to condition on a vehicle at the origin, but we don't want to include it in the interference. So that gives this Palm measure that we are interested in, and M indicates the vehicle order. Now, so we can analyze the general vehicle where M is 2, T-junctions, four-way intersections, and so on. Now, this is just to see what can be done and how messy it is if we do it. So that's the analysis for the Poisson stick process with the street of half lengths with density FH. So the SIR distribution looks like that. So that's a product of two Laplace transforms that model the interference of the one street the vehicle resides on and the others. And these are the two terms. Now, and we see that inside this term, there is another Laplace transform with an integral. So we have 5 nested integrals here. And also one thing I'd like to mention is because of the half-length distribution, we expect there to be an expectation over this distribution somewhere. And that is true in this case, that is true for the other streets, but the street that the vehicle resides on has a different distribution. Now that's F tilde. And that F tilde is given like this. So why is that? Now, so here we need to take into account that longer line segments on average have a larger number of vehicles. So the typical vehicle is more likely to be on a long line segment than on a short one. Now, so this is size bias sampling now that we need to take into account using this skewed distribution. So we call this too complicated. No, so it is exact, but it is hard to evaluate and it's hard to get any direct insight in how this system behaves as a function of the various parameters. So let's discuss for a moment. Now, so first we note that we cannot really ignore the street geometry. Now, just being agnostic of streets and put vehicles everywhere gives us the wrong picture. Now, the street system essentially leads to a clustering of vehicles. So we don't want to do that. On the other hand, now we can do an exact analysis as just shown, but the results are quite unwieldy. And so what can we do? No. We notice that the precise modeling of the interference that are far away is less critical. Now, we want to be accurate in the immediate vicinity of the vehicle under consideration, but we can be more generous further out. And that's what led to this idea of transdimensional modeling. So we want to model the typical vehicle's street or streets, if it's an intersection, exactly, namely as one-dimensional PPPs, but we ignore the fact that the other vehicles, the interfering ones, also sit on streets. We just let them be two-dimensional Poisson processes. So essentially, we have a combination of 1D and 2D Poisson processes now, and that's why we call this transdimensional. It's a fancy name just for saying, okay, yeah, we have 2-point processes, one of dimension 1 and the other one of dimension 2. So in the case of a Poisson line process, we just take the line that the vehicle at the origin sits on, that's the red one, and everybody else is just a Poisson process. Now, if we think about how we analyze this Poisson line process model, now it's kind of natural to add this street, because when we look at the Palm measure of this process, by conditioning a vehicle to be at the origin, we automatically require a street to go through the origin. Otherwise, the vehicle cannot be there. So in some sense, this is the street that we now explicitly model that otherwise is included in the Palm measure. Now, let's compare the analytical expressions. Now, we'll see this for sure a bit later too, but if we take the Poisson line process, we can get an expression like this for the SIR distribution for vehicles of order m, so m is 2 or 4. So we have a part that comes from the one street through the origin, and then a part that comes from the others. And in this case, this is a double integral. We compare this with the transdimensional version. Now we have a nice closed form expression now that just has these couple of gamma functions in it. So if we want to evaluate that with, say, some accuracy, 10 to the minus 9, this one is 5 orders of magnitude faster to evaluate. But how accurate is it? Here is a plot for a Poisson stick model for general vehicles. That means m is equal to 2, density 1. And we have the exact plot. These are the crosses. And we have the transdimensional one. These are the purple curves. Now, so they're very, very close. And moreover, they are asymptotically exact as the SAR threshold theta goes to 0 and also as it goes to infinity. Because when we let theta go to 0, what matters is really the immediate neighborhood only. Because only when a vehicle is really close, we do not succeed. On the other hand, when we let theta grow, we need, in order to succeed, we need a large region to be empty. And what the vehicles outside these regions are, whether they are on streets or not, doesn't matter anymore. No, so in this case, it's really only the two-dimensional PPP that matters. Now, if we look at the intersection vehicle in a Poisson stick model, now then by conditioning the vehicle to be at an intersection, now that means we need to have 2 sticks going through the origin. Now here we draw them orthogonally, but they could be drawn at an arbitrary angle. And this is a comparison again for the exact stick model and the transdimensional approach. Yeah, we get a tiny bit of a difference in some regime. In fact, if we plot the difference over the entire range of parameters, now which here is relevant is the distance and the SIR threshold and the vehicle density times the transmit probability. Now we see in most of this region, the difference is very small, and there is one point where it reaches about 0.03. No. And something we want to keep in mind, now, even though we have an exact expression, it consists of 5 nested integrals, which when we evaluate them numerically, we never get an exact result. No, so there's going to be some error in there naturally, no, because in a finite amount of time, we cannot evaluate with arbitrary precision. No, so if we put constraints on the resources we have to evaluate, it might be that we end up with a better result using this simple approach than with the seemingly exact approach. Okay, now let's have a close look at what we have actually analyzed so far. So say we have a probability SAR exceeding theta to be equal to 0.9. What does that mean exactly? So now we have averaged over all the fading, over the vehicles, the street system, and so on. But the thing is, now a statement like that doesn't really tell us anything about the reliability of any link in the network. So, for example, it doesn't tell us what is the fraction of links that achieve theta with probability 0.9. There's no link in the network that has this reliability. The only notion of link to which this applies is the so-called typical link, but no link is typical in the network. Now, that is an abstract notion corresponding to the average. So what this tells us is really only that 90% of the links in any time instant happen to achieve an SAR of theta without any reliability information. Moreover, these links are going to change from time slot to time slot. It's not that a vehicle now is going to achieve this, and if it does once, it does forever. No, that changes because of the fading. So, in other words, there's no information about individual links. We cannot guarantee anything. Now, let us for a moment fix the point process and only average over the fading. So these are the per vehicle SAR distributions conditioned on the point process. And then we can, for each vehicle, we get an individual reliability. And with that, now we can plot a histogram. And see how there are some vehicles near 1, there are some vehicles around 0.8, and so on. So this is for a case where lambda times p is 1/8 and the transmit probability is 0.1. If we change that, we keep lambda times p, but we change the transmit probability to 0.9, while of course reducing the vehicle density, we get a very different histogram. But the standard analysis gives us only one result, and that's the red line. Oh, 0.9. Here, same thing, 0.9. But the behavior of the network is very different, no? Because here we can say, okay, pretty much every vehicle at least is 60% reliable. And here we have a good fraction of vehicles, now maybe 20%, that don't even achieve 0.6. So what we want is, instead of just capturing this red line, we want to capture the distribution. We want to capture this histogram. So we want to capture the distribution of the conditional SAR distribution. And in so doing, we are nicely separating the temporal scales and the spatial scales, because we first average over time the fading, and secondly over space, the point process. So this brings us to the concept of meta distributions. So this is broad, no, for a moment, not tied to stochastic geometry or point processes. So this is the way we can think about this. If we have a random variable, z, that is a function of two other random variables, x and y. So if we focus on z, of course, we can talk about its mean. We can take the expectation. If we want to have more information, what do? We add an indicator, we add a dummy parameter, the little c, and we get to this indicator here. The expected indicator is what we call the CCDF, complementary cumulative distribution. And then if we want to go back, we just integrate over the little z. Now what we are doing in the meta distribution, we just take this one step further. We take another indicator, this time with respect to x only, we add another dummy variable, and we get this. So that's a meta distribution, a distribution of a conditional distribution that now has two parameters, c and x. And now to see that what we have done before is really just an average, we can introduce a new random variable u, that is the conditional distribution given y. Then the CCDF is just the expected u, and this meta distribution is the distribution of u. So this is the notation that we use. That's the meta distribution of z, where we first condition on y. And instead of using the expectations of indicators, now we can write this using probabilities in this form. So here is a toy example. Now, if we take a ratio of two independent exponential random variables, we are interested in z, which is this ratio x divided by y. we can immediately calculate the distribution. Now this one doesn't have a mean. We introduce the new random variable, that's the conditional distribution. And then by averaging over y, we get the meta distribution, which now has two parameters, x and z. And then we can retrieve the original CCDF by integrating. So if we actually consider x and y, the distribution of z is just the mean, while the meta distribution is the distribution. So if we want to learn something about the inner structure of z, namely how it depends on x and y, now we can use this form of a distribution. So if we apply this now to the vehicular setting, if you assume the point process is constant, now for the time duration of a transmission, we get this double palm measure, which again separates time and space, and it reveals this per vehicle statistics that corresponds to the histogram before. So this quantity, this meta distribution, now indicates the fraction of vehicles that achieve an SAR of theta with probability of x in every single realization of the point process, thanks to ergodicity. So that is a very strong metric. If we take a derivative with respect to x, of course, we can retrieve the histogram that we've seen before. And if we invert this in x, we get the reliability that a certain percentile of vehicles achieve. So if we take the inverse with respect to x at 0.95, it gives us the reliability that 95% of the vehicles achieve and 5% do not. And then if we want, we can go back to the standard SAR distribution by integrating over x. So there's a few simple cases now where we can get a closed form result. Assume that vehicles try to communicate to a base station infrastructure, and the base stations form a Poisson process of a certain intensity. Connecting to the nearest one means the distance there is Rayleigh, now with mean 1/2 square root lambda. We assume a free space path loss, so the signal power is given like this. In this case, now we can get a very simple expression for this meta distribution of the signal strengths only. So we can plot these blue curves, and they give the fraction of vehicles for which the signal power exceeds theta with probability at least x for each realization of the base station process. So in this case, at this point, we see 80% of the vehicles achieve a signal strength of 1 with probability at least 0.6. But now if we wanted to incorporate interference from a large or infinite set of interferers, we cannot get a direct solution for the meta distribution. But what we can usually do is we can calculate moments of this conditional distribution. So that's just by nature of the tools that we have from stochastic geometry. And then once we have the moments, now there are different ways to retrieve distributions. Now a popular one is due to Gil Pellais using imaginary moments and calculating this integral. It's nice analytically, but this never has any closed form solutions, and it can be tricky to evaluate because it might not decay that quickly. It might diverge at 0. So we have to be careful numerically. If we calculate integer moments, now then the problem of retrieving distribution is called a Hausdorff moment problem. In practice, we only have a finite number of moments that we can calculate, and then it's a truncated Hausdorff moment problem, in which case it usually has infinitely many solutions now, and then we can calculate infima and suprema over the set of possible solutions now. So this is a part of ongoing research. Now, often a simple beta distribution approximation where we match the first and second moments now gives quite good results, or even just the variance now tells us something about how concentrated the performance is. So we assume we can calculate the moments, and indeed, if we take the transdimensional approach, we get simple expressions for general moments. So here B can be any complex number. Now, so it looks similar to the previous expression for just the SIR distribution, with the difference that now we have this hypergeometric function here involved, where the parameter b shows up in 2 places. No, but still, now we can call this quasi-closed form, and we can evaluate this quickly. And of course, if we went back to the PLPP, now we have a double integral to start with, and then that gets further complicated by the arbitrary moment that we would like to calculate. So let's see how accurate the transdimensional approach is for this meta distribution. Also, here is a comparison again between the Poisson line process and its transdimensional version. If we set the reliability threshold at 0.6, we can plot this meta distribution as a function of theta, and we see that in this regime of high reliability, now which is the most relevant, we get again asymptotically exact results, and only down here we get a bit of a gap, but that's not the region where we want to operate a network. So we set, say, the threshold equal to 1. The standard SIR distribution says 0.7. So we know in this model 70% of the vehicles succeed, but no information now about individual vehicles. In contrast, the meta distribution tells us that 0 dB, now theta equal to 1, 82% of the vehicles are 60% reliable, and 27% of the links for vehicles are 95% reliable. So we get very fine-grained information. Shadowing. No, okay, so now we have only Rayleigh fading and distance. If we introduce shadowing, the accuracy of the transdimensional approach increases further. And that's because now shadowing essentially is like a perturbation of the locations. If shadowing increases, the point process tends to approach that of a Poisson process, which we already have here. Now it's similar as has been established by Bartek and co-authors know that for cellular networks with enough shadowing, everything looks Poisson. So a little application of that. In congestion control, now we would like to adjust the transmit probability as a function of the vehicle density so that we can maintain a constant reliability performance. Now, if we did that using just the standard SIR distribution, we realize, oh, that really only depends on the product lambda times p. So choosing p in proportion to 1 over lambda is going to keep the SIR distribution the same. So if we plot this, now so here we inverted lambda, we plot 1 over lambda here and p here. Congestion control means, oh, we just have straight lines. So we want to have 0.9 in the overall success probability. Now then we choose, for example, if we have the density 1/4, we choose a transmit probability of 50% and we get there. We follow this line. But that means if we do this, we are changing the fraction of links that achieve a certain reliability. So instead of looking at this, we should look at the meta distribution. So that we can maintain, say, 95% of the vehicles achieving a certain high reliability. If we do that, these curves are no longer straight lines. So now they are bent and convex or concave, depending on the reliability threshold. Now, in the higher reliability case, these curves look like this. So quite non-linear. And we realize now that once theta exceeds the threshold, so if we go to the left here, we might have to quite drastically reduce the transmit probability to maintain a certain performance. Now, so this derivative here might be infinitely steep, so there needs to be a big reduction to maintain performance. Last comment here. So far, we have assumed a fixed distance. Now, of course, with a random vehicle model, if vehicles talk to each other, distances become random. Now, we could add another continuous parameter, but perhaps a better way to take that into account is to use distance bins. So we want to know, okay, what is the behavior of vehicles that are within 50 meters or between 50 to 100 meters and so on. So with that, now we get a finite number, say 6 individual meta distribution. for each bin. And this is just an example where we did a comparison with an NS3 simulation of a protocol that Toyota came up with a few years ago. That's called Limerick, which is some kind of carrier sensing mechanism for the DSRC protocol. And in this case, now we realize that the PPP model no longer does well. And that, of course, is to be expected, because now the transmitting vehicles do not form a PPP, but a more repulsive point process, which can be modeled using a so-called determinantal point process on the right here. So this is this kind of extension to non-Poisson processes is part of ongoing research. So in conclusion, modeling the streets is important. However, modeling all streets is not that important. We need to carefully model the streets that the vehicle that we want to focus on lies on, but not the others. So this leads to this transdimensional approach, using which we can get nice approximate results for fairly general models and intersection orders. You want to keep in mind that the numerical evaluation of many nested integrals over infinite ranges is tricky and doesn't really give us full accuracy, full precision in practice. Now, in particular, in the high reliability regime, where the transdimensional approach is asymptotically exact, the TPTP results, the transdimensional results might be more accurate than the ones you obtain from exact analytical expressions that we need to evaluate. The two-parameter meta distribution addresses the inadequacy of the standard SAR distribution in quantifying reliability of individual links. And generally, in stochastic geometry applications, the wireless is obtained by a Hausdorff moment transform. Now, because of the simplicity of the approach, we can hope to extend this to non-Poisson deployments, which is work in progress, which might be somewhat hopeless now if we try to do this strictly in exact form. This concludes my talk. Thank you. The session chair is moderated.
Okay, all right. Please.
Okay, let me give it up. Thank you very much for the very interesting talk. I have a question a bit aside from what you presented, if you don't mind.
Sure.
You were talking quite in depth about modeling the streets and their configuration and so forth for particular systems. The question is, maybe you do know, starting from which level of granularity modeling the vehicle itself becomes important. Like, because the vehicles are of different sizes, they could be buses, they could be trucks, the antenna placement could play a role, and something like that. Are there any good techniques that are already adopted somewhere, or maybe, or if you could speculate, like starting from which distance should I care and from which scale I shouldn't? Thank you.
Yeah, so part of blocking and different vehicles could be incorporated in fading models. You could say, okay, there's a certain probability I have a big truck between two vehicles, which means there could be a change in the fading model, and say, okay, with probability 0.05, the link is essentially broken. And then one has to incorporate that fading model. It's the same when you have two vehicles that are seemingly close, but they are both approaching an intersection. There's a big building in between. Now you have this kind of shadowing. Generally, as long as you can represent it in a nice stationary random way and say, okay, there's a fraction of vehicles that are big and there's a fraction of vehicles that have a broken antenna or whatnot. Then it's not that hard. Although deviating from Rayleigh fading is a significant step. Because the Rayleigh fading has this exponential distribution that really gives access to a nice set of tools. But from what we've learned, whatever you do, if you start with something more simplified, like a transdimensional model, compared to something complete and exact, to have a higher chance of incorporating these finer aspects of vehicular networks. So this just happened very recently now, and I think it would be interesting to see how far we can push this now in terms of modeling other aspects. Yeah.
Thank you very much.
Yeah, I noticed that the curves that you produce for the property of coverage in your transdimensional analysis and the true ones were ordered always the same way,
Yes.
if I'm not mistaken, and with the true model dominating in terms of variability.
The transdimensional approach gives a lower bound. Yes.
Yeah, right.
Yes.
So is it a general result? Is there a proof?
We have proved it in some cases.
Okay.
No, not in all generality. No, but it's kind of intuitive based on the fact, okay, that you forget about the clustering of the interferers. So you are exact now in one street, and then you look at what is the effect when you model the interferers as just a Poisson process instead of a clustered process. We were able to look at distances to nearest interferer, second nearest. Now we're able to prove that in some cases the TPP is always conservative. That the interfering vehicles are closer on average. So we have a partial answer to that, but it seems to hold pretty much everywhere, which is good for practical purposes. Now we want to have a tight lower bound, rather than an upper bound where we don't know how bad things might be in reality.
So if I get it correctly, this keeps the mean in terms of the interfering pattern.
Yes.
But the variance is certainly less.
Yes.
You have, and so it could be linked to this fact that variance, increasing variance is good for many of these models, right?
Yeah.
Which is a very surprising fact compared to what we learned in theory.
Right? Yeah.
In obstacles, it's also the same.
Exactly.
That's interesting. Thank you.
Further questions?
Are there comments about the impact of the different sections of the performance when
Oops, there is a...
Yes, that one. Speak louder.
Okay, I think I can. Yeah, so the question is the impact of the order M. And what we see now, I didn't highlight this really, but what we see is that the intersection order really only affects the streets that the vehicle at the origin resides on. So we typically get for each street that goes through that vehicle, we just get an extra factor M here. So if M is equal to 1, then the streets extends in one direction. If M is 2, it goes in both directions. If M is 4, we go in 4 directions. If M was 6, it goes in 6 directions. So now we can say, even though we don't have a good model for 6-way intersections, if we did, we knew what the transdimensional version would look like. If we want to analyze and say, okay, we have Place d'Italie now, which has 10 streets going out, we put M equal to 10, and immediately we have a result for a vehicle at a 10-way intersection in the transdimensional version, even though the underlying street system does not really exist. Or you would have to think really hard to come up with a reasonable model that has 10-way intersections. So typically it's really just a factor here inside this exponential. And this also translates to the meta version here. So that's the first term for the streets that the vehicle sits on that has a factor M here in front. So it's quite simple now to take this into account.
Further
Question.
Oh, sorry.
So it's more a doubt than a question. So what is known is that there should be some time and space correlation between the performance of objects. So in this case, is a signal that we. So the model you have shown basically studies the system like it was completely random with not much correlation between. I don't know if this is important or not. I'm pretty sure that time correlation is not important because you have this validity property of what you are studying. I wonder if the space correlation of vehicles may be important or not, or if it is an approximation that may be not important, or if it is important, if it can be incorporated in the model.
Yeah, I think there are several aspects. Now, one is the correlation in the vehicle locations, which here is considered using a so-called determinantal point process. Now, where especially as vehicles get more congested, now we have to be more careful in who gets to transmit, and we want to space the concurrent transmitters more accurately. Now, in terms of space time, now I think if we want to for sure get a message across, now then things become temporally correlated also, because then if we don't succeed, we have to keep trying, and then we are more likely to be active. Actually, I believe now maybe in the next talk, some of the spatial temporal aspects are going to be addressed. Now I think Jong-Sik has some work now incorporating that. So some of that can be done and should be done. Now we are just in our own work here. Now we are not at that level yet. Now we are starting to look at correlations in the vehicle positioning. No, but we haven't gone further than that. I think when you look at cellular networks or ad hoc networks, now the work on correlation issues is more progressed at this point.
Yeah, it also depends on the frequency you're using to transmit.
Yeah.
But definitely there's a tendency towards having higher correlation when the density increases. So depending on the frequency, the density threshold may change.
Sure. Yeah, I mean things are sparse now. They are more accurately modeled by assuming levels of independence, in time and space. Yes.
But it looks like correlation may be incorporated in the way you generate the distribution or the distribution, I guess.
Yeah, I mean, in some way, now this transdimensional idea shows that correlation is not as important in some part. Now we can ignore the fact that interfering vehicles are correlated due to the underlying streets. Now, without much loss in accuracy.
Yeah, but
no, I think
of the local area around.
Yeah, sure. Yeah, there definitely. No, it needs to be taken into account. Yes.
Thank you.
I will. Okay, then there's some literature on stochastic geometry and tessellation, various kind of tessellations, even iterated. This was done to fit the fixed telephony structure and to optimize some. But I wonder, is it possible to use these models, and for them, would it be possible to calculate your characteristics and to see whether they are the same or not with respect to mobile networks?
I think so.
So would it be much harder to calculate, like for example, the support being the edges of the Voronoi tessellation will be more complicated than just Poisson line or Poisson sticks? And I imagine that it's much harder than having.
Yeah, definitely. I think if you want to be exact,
Okay.
no, I think it would get complicated. No, but maybe there is another good idea. No.
Way to approximate these models.
Yes.
There are some body of models that are somehow developed and maybe of use in this context.
Yeah. I agree. I mean, the general idea of kind of being locally exact and globally approximate, now I think is a promising one. Now that kind of can unlock more. Gives access to more interesting models that otherwise just seem to become hopeless. Yeah.
Okay, I don't think there's further questions. I don't know if there's questions from people online.
There's one question in the chat. Okay, so not related with it. Okay, well then let's thank Martin again for the next one.
Thank you.